Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the introduction of spectrophotometer. And introduction of the spectrophotometer, we just discuss about how that spectrophotometer is work or the working of the spectrophotometer. And as we know that UV spectroscopy, it is UV spectroscopy provides us the information about the structure of the molecule that contains or which contains double bond or triple bond or conjugated bonds. And this spectroscopy also provides the information about isolated double bond or conjugated double bond, trines or dienes, or carbonyl group, as well as alpha beta unsaturated carbonyl groups. So it also throws the information regarding the stereochemistry, like as a special type of the isomer which is known as a geometrical isomers. And as we know that geometrical isomer means what? The restriction is rotated, the rotation of restriction of rotation due to the presence of carbon-carbon double bond gives rise to a special type of isomer which is known as a geometrical isomers, such as cis isomer and the trans isomers. Cis isomer means the similar group are on the same side of the carbon-carbon double bond is termed as a cis isomer, whereas trans isomer, the similar group are on the opposite side of the carbon-carbon double bond is termed as a trans isomer. How quickly it provides the information regarding as a cis and trans. Cis absorb or gives lambda max, is lambda value is less as compared to as a trans, or a trans isomer always shows the lambda max greater than the cis isomers. So in this way we can get quickest information from the UV spectroscopy. And how the instrumental part, and there we have seen some of the important point as far as the exam point of view is concerned. The cuvette in analytical chemistry, generally we see it is a special name given to that container. It is the smallest test tube which is known as a cuvette. Generally it is used in a colorimeter or UV spectrophotometer, which containing sample or what we can call it as a reference compounds. Here generally the solvent used in for the dissolving purpose, like N-hexane, water, distilled water, 1,4-dioxane, 95% ethanol. Absolute ethanol does not use in UV spectrophotometer. The reason we know that, the reason behind is very simple. While the synthesis of absolute ethanol, it requires the benzene, and when we are synthesizing or when we are preparing absolute ethanol, the traces amount of the benzene contain that absolute ethanol, and due to the presence of traces amount of the benzene, as we know that benzene is a chromophore, and as we know that chromophore, it is a functional group capable of absorbing UV radiation, and therefore the peak is observed at 255 nanometer, and it will interfere, it will disturb the spectra, the desired spectra we won't get due to the interference of that benzene, and due to this reason absolute ethanol cannot be used in a UV spectroscopy. Another important question we have learned, glass is not used to manufacture or for the making of cuvette, or that what we can call it as a sample holder, sample container, not holder, sample container. Sample, if the sample container contains glass, it will absorb UV radiation strongly. It also disturbs the spectra. We won't get desired spectra, and therefore the special material is used to prepare, to make the sample container, like quartz or fused silica. These are the material generally used to make the sample container. That is the reason behind it. So now today what we are going to discuss, let's see over here, vacuum ultraviolet. As we know that the range of ultraviolet visible spectrophotometer or spectrophotometry starting from 200 nanometer to 800 nanometer, that is a general reason. But if you see the particular UV region, it is starting from 200 nanometer to 400 nanometer, which is a region for ultraviolet, and for visible very narrow region 400 to 800 nanometer, which is known as a visible region. Why it is called as a visible region? Because whatever radiation fall in that region, that object we can observe or we can see by our naked eye, and those are above or below that range we cannot observe, we cannot see the material or the object. And vacuum ultraviolet, it means what? For UV, you can call it, or for generally the conventional electronic spectroscopy technique mentioned above cannot be used below 200 nanometer, because the radiation are absorbed by air due to presence of moisture, and also due to electronic transition below 200 nanometer. For UV, one must use vacuum apparatus, and therefore This for UV region below 200 nanometer is also known as vacuum region. Generally 165 or 190 below 200 nanometer is known as a vacuum region, that you must remember here, maybe as a 165 nanometer or 167 nanometer or 190 nanometer. These are known as a vacuum region. The UV spectrum of 10 depend upon number of variable such as solvent, concentration of solution, and length of the solution through which light passes. The amount of light absorbed by particular solution is quantitatively determined by Beer-Lambert's law. That is Beer-Lambert's law. As we know that this is one of the well-known Beer-Lambert's law. It is simply is, suppose we have this rays, here is a one cuvette is kept over there, sample in cuvette. You can see over here, sample in cuvette. Look at the spelling CUVETT. Similarly, vacuum also VA, not VO. That is VACWM, vacuum. So cuvette, and here another ray. As we know that here is a light source. Generally source of light, this you can call it as a source of light, and there is a monochromatic light is passed, which is known as I0. I0 is called as the incident light, which is known as a incident light, and when transfer from this, which is known as I, it is a transmitted light, and therefore it is called as transmitted light. This one is called as a transmitted light. And according to as the absorption of light energy by the molecule is governed by the famous Beer-Lambert's law. To understand these laws, let us first define a quantity known as absorbance. Absorbance, and that is denoted by A, as we know that. So absorbance, consider a radiation of light by the molecule is governed by the consider a radiation of light incident on a sample kept in a tube. In spectroscopic language, it is known as cuvette. The sample absorbed part of the incident light and transmit the rest. Let I0 be the intensity of the incident light. I0 is the intensity of the light, and I be the intensity of the transmitted light. And therefore absorbance for optical density as known earlier is then defined as the log of the ratio of intensity of incident light and transmitted light. A is equal to log of I0 upon I This is a general, this we can call it as equation number 1. A is equal to absorption log I0 is intensity of log I upon I, that is I0 is the Beer-Lambert's law states that absorption of a sample is directly proportional to its concentration C and to the path length of the light L through the cuvette, which is A equal to C into L, which is the equation number 2 here you can remember. Then and therefore A equal to, A is directly proportional, so epsilon CL, that is the equation number 3 you can remember, where A is absorbance, where A is equal to absorbance, epsilon is nothing but as extinction coefficient, and C is a concentration of solution, so concentration of solution in moles per liter, and L is the path length. These are the, and E is known as a molar absorbivity of the sample, old term molar extinction coefficient. The epsilon value is constant for the given sample under the given set of condition. Its value is very much dependent on solvent used to prepare the solution of the sample. We will discuss the significance of epsilon values in the next section. So before that, let us see another point: energy absorption and electronic excitation, that we are going to discuss over here. Just now we have seen as this law. Now let me explain another point here, that is energy absorption and electronic energy absorption and energy absorption and electronic excitation, excitations. That is a point of discussion: energy absorption and the electronic excitation. As we know that ultraviolet and visible radiation are more energetic, absorption of these radiation by an organic compound brings about electronic excitation. The process of electronic excitation is accompanied by a large number of vibrational and still large number of rotational changes. It is hardly possible to resolve all these spectral bands which get mixed together, and therefore here remember it is a very prominent or the important point. Therefore bands in UV spectrum are relatively broad. The total energy required for excitation of a molecule from ground state to excited state is given by E total is equal to E electronic plus E vibrational plus E rotational and plus E translational. Translational is negligible, that's why we cannot consider over here. So why we are getting as a broad spectra in UV? Here generally the inner absorption versus wavelength means lambda, so we are getting as a such type of the broad peak that is known as a lambda max. Why we are getting broad peak in UV spectrophotometer? The reason behind it is very simple. When the ultraviolet radiation strike to the molecule absorb part of it that goes in the higher energy state, mean in the excited state, there is a electronic excitation takes place. The amount of energy absorbed by that molecule is responsible for electronic excitation, and that depend upon the structure of the organic molecule, and therefore the total energy is equal to E electronic plus E vibrational plus E rotational. Whenever there is a electronic excitation takes place, along with there is a vibrational excitation as well as a rotational excitation, it is a very difficult to resolve electronic excitation separately, and therefore that electronic excitation consists along with vibrational as well as rotational, and due to this all together we are getting the broad spectra in UV spectrum or in a UV spectra. So that is one of the important point you must remember here. Now is a electronic excitation. How do you define electronic excitation? Just now I told you that the molecule absorb UV radiation, the energy associated with is responsible for electronic excitation. When it goes in the higher excitation state, the absorption of electromagnetic radiation of wavelength, as we know that 200 to 800 nanometer UV and visible region, can cause excitation of electron from occupied bonding molecular orbital lower energy to unoccupied antibonding molecular orbital higher energy. This excitation is called as electronic excitation. Just now we have seen this is a electronic excitation means what? How do you define the electronic excitation? This is the electronic excitation is called as electronic. Just now we have seen this one means the ground state electron which is known as a bonding molecular orbital, that is fully occupied and unoccupied. LUMO and HOMO and LUMO, you might be heard this word. HOMO means highest occupied molecular orbital, LUMO means unoccupied molecular orbital, and whenever there is a ultraviolet radiation absorption takes place, the bonding molecular orbital, that electron goes in the excited state, and that excitation is known as electronic excitation. And we know that there are three kinds of electron present in molecule. For example, sigma electron present in sigma bond, as we know that. This one also. What is that? Sigma electron. There are three kinds of electron present in the molecule. Number one, sigma electron present in sigma bond. Sigma electrons present in sigma bonds. As we know that sigma bond is made up of by sharing of two electrons, and when sharing takes place, maximum electron density present in between two nuclei, it is a coaxially overlapping takes place, and therefore sigma bonds are generally stronger as compared to as a pi bond. Pi electrons present in pi bonds. Second one, pi electrons present in pi bonds. Present in pi bonds. As we know that pi bond is formed due to the lateral overlapping between two atomic orbitals, and the electron present in that is known as a pi electrons. Lateral overlapping or the sidewise overlapping, and due to this reason very less amount of the electron density present between two nuclei, and due to this reason pi bond require very less amount of energy to break that bond, and due to this reason generally pi bonds are weaker than the sigma bond, or other way round we can call it, sigma bonds are stronger than the pi bond. So that is the, and now the number 3, which is known as N, means non-bonding electron present in unshared electrons. Non-bonding electrons present in unshared electrons. Present in unshared electrons. And these are the three main type of electrons present over here. So I think with this let us stop today here. Remaining how that electronic excitation, which are the major excitation or allowed excitation, and what type of the organic molecule shows transition or the excitation, for example sigma transition, which are the allowed transition, which are the forbidden transition, and what type of the organic molecule can shows what type of the transition, that type of questions answer we will find in the next lecture. I think with this let us stop today here. Remaining we will see in the next lecture. Thank you. Have a nice day.